This problem asks us to evaluate a number of limits. I've changed the order of the parts just to help the exposition a little bit. Part C wants us to find the limit as x approaches 2 of some polynomial. Whenever we're finding limits of polynomials as x approaches some finite number, we just plug that number in, right? Polynomials are continuous, so evaluating this limit is simply plugging 2 in for all of our x's. So this is 4 times 2 cubed minus 2 times 2 minus 3, and that's equal to 25. Okay, again, polynomials are continuous everywhere, so to find the limit as x approaches some finite number, just plug that number in. Part A wants us to find the limit as x approaches 2 of a rational function. X squared minus 3x plus 2 over x minus 2. Now our plan of attack with finding limits as x approaches some finite number of a rational function is to simply start by plugging this number in and seeing what we get out. If we get a number, then the limit is simply equal to that number. If we end up dividing by 0, then we have to do a little bit more work. So let's go ahead and plug in 2. And in this case, we are going to get 0 in the denominator, but we are also going to get 0 in the numerator. When we get 0 over 0, which is called the indeterminate form, this rational function might have a limit at x equal to 2. There might be a hole in the graph for this function. Now, because we got 0 over 0, we know that x minus 2 must be a factor of the top and the bottom. So let's go ahead and factor and see what happens. The top factors as x minus 2 times x minus 1. And we see that the top and the bottom both have a factor of x minus 2. When we cancel, we are simply left with the limit as x approaches 2 of the polynomial x minus 1. And so to evaluate this limit, we simply plug 2 in for x. And we are left with this limit being equal to 1. So let's look at another variation of that type of problem. Part E wants us to find the limit as x approaches 6 of x over 2x minus 12. Again, we have a rational function here, so we're just going to go ahead and plug in 6 and see what happens. In this case, we get 0 in the denominator, but we get 6 in the numerator. And this is an undefined form. We have a non-zero number in the numerator and 0 in the denominator. And when this happens, it indicates that this rational function has a vertical asymptote at x equal to 6. And for us, functions or rational functions do not have limits at vertical asymptotes. So in this case, the limit simply does not exist. Right? Now the third situation would be plugging in some number into a rational function and getting a number out. When that happens, that number is the limit. This question has 2 more parts involving limits at infinity. Now it does not matter that When we're finding limits at infinity for rational functions, it doesn't matter whether we're talking about x going off to positive or negative infinity, the analysis is going to be the same, right? And the idea is just to stare at the degrees of the numerator and the denominator. Remember, the degree is the highest exponent on x. So here the degree is 3. The degree of the numerator is 3. The degree of the denominator is 4. Because we have a larger degree in the denominator is just going to pull this entire function closer and closer to 0 as x gets large. So this limit is equal to 0 since the rational function is bottom heavy, right? The degree of the denominator is larger than the degree of the numerator. In part D, the degree of the numerator is 2, and the largest exponent in the denominator is also 2. Right? So here we have a situation where the numerator and the denominator have equal weight. So the limit is just going to be the ratio of the leading coefficients. The leading coefficient here is 3. The leading coefficient of the denominator is 1. So this limit is equal to 3. Okay. And of course the other possibility for limits at infinity of rational functions would be the degree of the numerator larger than the degree of the denominator, and in that case the numerator will drag the function off toward positive or negative infinity. So if the degree of the numerator is larger, the limit does not exist.